The lecture yesterday, some of you, are we okay? Yesterday at the end of the lecture, we were working on a problem number 86 on page 315 that had pi in it, and some of you zoned out. I think you were in brain overload. So we're going to pick up on that today to clean that up. And then I'm just going to revisit a couple of things that we did yesterday to make sure we're clear. We're going to look at graphing based on the transformation, make sure we got all of our terms straight, which is kind of a review, increasing, decreasing, max, mins, kind of stuff, vertex, axis of symmetry. Then we want to make sure we're good at graphing just a quadratic function. Remember, we skipped objective 1, which required completing the square, which actually gets it back up to the form a times x minus h squared plus k. Now, if you already know how to complete the square, you are very welcome to do that, but we're going to go with the option 2 in the book. Then I want to go to the exercises in section 3.1 and make sure we're good at some of those. Of course, we're doing already number 86 on page 315. And then for today, I ask you to make a sketch of these curves. Just get these curves, each one on the coordinate system. And if you're doing this by distance ed, this should be on the Vista link for you. And we're going to sketch these and learn how to, this is a very calculus related topic, so you're guaranteed to have this on your test and guaranteed to have this on your final exam, very calculus related. In calculus, finding the area of regions bounded by curves is an important concept. It's extremely important. And so pre-calculus is going to lay the foundations for this concept by sketching the curves, shading the bounded region. We want to be able to identify that bounded region. And then we're going to use algebra to determine the points of intersection. And we're going to use just one method, which is substitution method, to do it. We'll talk about that. So this is laying the foundation so that once you get in derivatives, the application is to integration, areas bounded by curves. You'll be all set, ready to go. So that's where we're headed today. And again, in lecture 7, we will start out, hopefully, with specific questions that you have, okay, as a review for your test. Of course, we'll talk through the book some, too. All right, the first thing we're going to do is head back to page 315, number 86. That was at the end of class yesterday. 315, number 86. This is in section 3.1. This was where we had the window, as you'll remember. That was the shape of a rectangle at the bottom, had a semicircle at the top. And what happens is that they needed the perimeter of the window to be 20 feet. But they wanted to maximize the area here so that more sunlight comes in. And in calculus, you will also use derivatives to learn how to do this. But in this class, this is going to end up being a quadratic function, and you know how to find the vertex of a parabola, which is where you're going to find your max or min. Okay, so if you look back to your lecture 5B notes, we had worked our constraint equation with our circumference. That was with our perimeter. Perimeter was 20 feet. And that went around the rectangle on 3 sides, plus half the circumference of a circle. So that's where we were constrained. We could only use 20 feet of a perimeter of 20 feet. Okay, but the function we needed to work with was area. So we have an area of a rectangle and area of a half of a circle. Area of a rectangle was length times width, and there's the area of half of a circle. And you'll remember that this function A now has too many variables in it, and we need to get it in terms of one variable. Well, you knew the relationship between the radius and the length. The radius of this semicircle is half the length, and I cautioned you to be careful that when you replace this R, that it's the entire R that is being squared. And I can tell you in calculus you have this problem, and there'll be at least 20% of the class that would do 1/2 L squared, and they would forget to square the 1/2. So don't let that be you when you get to your calculus class. Everybody sees what's going on here. Okay, so I made that substitution, and of course 1/2 times 1/4 was 1/8. So then we were down to A equals LW, and so now I've written area in terms of length and width, but I need to write it all in terms of one function. So we went and visited our constraint equation, and I believe this was it right here. We solved for W because that looked like the easiest thing to do, solve for W. And so I came right here and put in what W was. Okay, so far the process is not bad at all. Do you agree? All right, then I flipped the page. Actually, I ran out of space, so I went to the blue sheet. All right, so when I went to the blue sheet, I multiplied the L times the 10, the L times the L over 2, the L times the negative pi over 4 times L. And so is everybody good to right there? All right, so then that's when I started getting glazed eyes in here. So I decided, okay, well, let me see if I can make this a little better. So instead of working here where I was trying to get a common denominator, I'm now going to pick up from there. All I did was recopy that so I could see it. Oh, I know what I did. Because sometimes people, L squared over 2 is a little confusing, I wrote that as 1/2 times L squared. And there's my pi over 4 times L squared, and there's my pi over 8 times L squared. So sometimes it's easier to see the coefficient instead of the division. Remember, division is just inverting and multiplying. Everybody good? All right. Now that's where I want to pick up here, because we're really trying to make this look like our good old quadratic function, something like y equals ax squared plus bx plus c, because then we know how to find the vertex, etc. of the parabola. All right, well, L squared is a common factor of these last three terms. So all I'm going to do is factor out a L squared so I'd start to get it easier to look at. So I have 10 times L, and then I'm going to factor out the L squared. So pulling out the L squared, I'll have a minus 1/2, a minus pi over 4, and a plus pi over 8. All right, I just used the distributive property in reverse to factor out the L squared. Is everybody good with that? All right. When I started getting common denominators yesterday, that's where everybody zoned on me. So I decided, all right, this problem's tough enough anyway. Why don't we use our calculator to just approximate, and then it'll seem easier. All right, so I worked this out on my calculator. I went negative 1/2 minus pi over 4 plus pi over 8. I just punched that in my calculator. So I'm just going to go approximately 10L plus. So when I added these numbers on my calculator to get a decimal representation, I will get a negative 0.893, and then that's multiplied times L squared. Okay, so I'm just going to say that's approximately this. Pi is not an exact number anyway, so you're never going to get it to the exact measurement. All right, everybody good so far? So if I just change the order now, I get negative 0.893 L squared plus 10L, and that's my area function. So this looks almost like AX squared plus BX plus C, where the C is 0.
Is that the area of the length or the area of the width?
That is the area expressed in terms of the length. So in your, what we're going to do is find out what length our rectangle needs to be that will maximize our area. And once you know the length, then you can come back in and you can figure out your width, and you can also figure out your radius of your semicircle. Okay, is that good? Alrighty. So at this point now you're in great shape because it looks like a quadratic function. And just remind me How do you find the x coordinate of the vertex? X of the vertex? There was a little formula you were going to...
over 2a.
Negative b over 2a. So here, my unknown is L, so L is negative b over 2a, correct? Because my variable is L instead of x. All right, my b is 10, so I get a negative 10 over 2 times negative 0.893. Does everybody see the relationship here? And when you plug and chug that in your calculator, that is going to give you approximately 5.59 feet for the length. Okay? So by using the calculator to approximate those pi, your answer is not exact, but that's pretty close. So you're going to do about 5.6 feet for the length of your rectangular part. Okay? Now for your width, by the way, let's think about what the graph of this thing looks like. See if I see a red somewhere. If you were trying to graph this thing, along this axis you have length, along this axis you have area, length and area. And this is a parabola that's going to open how? Down. So the parabola is going to open down somehow. And so when you found this length to be about 5.6 feet, you're going to be at that vertex, and that's where you're going to have your maximum area. All right? And when you substitute back in earlier for width into here and punch away in your calculator, you'll find that the width comes out to be approximately 5.6 feet. The length and the width are pretty close to the same, I believe. Hope I did that right. Okay, I'm not going to guarantee that. I know this part's right. I don't see my work for figuring that one out. I'll put a little question mark there. Somebody can double check me later and correct me. But you just put in L as being 5.6 about, and right here, and it should come out, I think, somewhere around 5.6. I might be wrong on that one. Okay? The process, though, do you understand the process? Ask me some questions.
Will you go back over this step on the notebook paper?
Which one?
The next to last step.
This one?
From there to the last one.
Okay. All right. From here to here. Okay, so that let's see how many people do figure out what I'm doing. What happened from here to here?
Simplify. Common denominator. Common denominator.
Well, this is multiplication. 1/2 times pi times a fourth times L squared. So when you multiply, you just multiply fractions, numerators times denominators, correct? Mm-hmm. So 1/2 times a fourth is 1/8. So 1/8 pi L squared. You only have to worry about common denominators when you're adding, not when you multiply. Okay? All right, now, tell me what happened from here to here. Somebody tell me.
You substituted the width.
Right. This area had two variables in it. I needed to find a way to get it all in terms of L. So I came over here and found what W was and stuck it right there. Okay? Now, what was my next step on this right here? What was that next step?
Took that L all the way through.
Okay, I distributed the L times each term using the distributive property. I distributed the L. Okay. And then here we are today. All right. Now, what happened from here to here? Not a whole lot happened. I did something because I thought it might be easier to follow. What did I do from here to here?
Took your variables out the top.
Yeah, I just, instead of writing this as L squared divided by 2, I wrote it like L squared times 1/2 where you invert and multiply because I thought it might be easier to see that way. Okay? And then what happened from here to here? You just said that. What? Say it again.
Oh, you just took the variable out of the numerator?
All right, you factored.
Yeah.
You factored out a L squared from those three terms using the distributive property in reverse. And then what did I do from here to here? Everybody knows that one.
So,
Punched in my calculator. And here I just rearranged the order because you normally look at it as ax squared plus bx plus c, the descending powers of the coefficient. And I just saw for L because that was my variable, the vertex of my L of my parabola. Is that good? All right, any questions, anybody? All right, it looked like an awful problem. As long as you had that little calculator to help punch away, things were not quite as bad. And we're good. Okay, we're going to back up a second, though. And let's go back. We did this yesterday, but I want to do it one more time just to make sure we're good, where we can talk about the graph, talk about increasing, decreasing, max, mins, vertex, axis of symmetry, all that good stuff. Okay, so we'll revisit that first. Anybody want to help me make up the problem? We can do whatever you want to do. We're looking at something of the form y equals a times x minus h squared plus k. Anybody want to give me a function? What's your favorite number?
6. 4.
9.
All right, 4. I heard 4. X, what else?
9.
Minus 9 plus
Got the squared.
what?
Forgot the squared.
Oh, thank you. What else?
5.
Plus 5. Y'all really want to get me off the graph paper, I can tell. All right. Let's analyze this. This is the basic graph, y equals x squared. I'll do the easy part. What's the next thing?
4.
Vertical stretch factor of 4. On your test, you have to get, for the test for this particular class, I don't know if you're watching it by video, but I know I've made up it for this particular one, and you have to give words. So we got a vertical stretch by 4. What does this 5 do? Okay, vertical shift up by 5. And what does this do?
Horizontal shift
Horizontal
to the right.
shift. Good. Right. 9.
What if you did the horizontal shift before the vertical shift?
It'd be fine. Question was, can you do a horizontal shift before vertical shift? Yep. You don't have to do this order. I'm trying to do the same order on this video over and over and over so nobody's confused. All right. Okay, let's see. Shift to the right of 9 and up 5. I'm thinking that I better come way over here. Don't let me forget to ask all the questions about this. All right, so here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? All right, we'll just put in all of our little transformations. Okay, so we'll start out with y equals x squared. Can you draw that in your sleep now? Good. That was the whole purpose of doing so many of these. 0, 0, 1, 1, negative 1, 1. Okay. When we're going vertical, what y value? I just gave you the answer. We are working with the y values when we do a vertical stretch. So what am I going to do to these y values, everybody?
Plus 4.
Not plus 4. Factor means multiplication. Factoring, you're multiplying things together. Factors, multiply by 4. So we're going to multiply all these little y values times 4. All the y values times 4. All the y values times 4. Okay? So, of course, 0 times 4 is 0. So we're still at 0, 0. And now, instead of 1, 1, we have 1, 4. because 1 times 4 is 4, and negative 1, 4. So we're like doing a vertical stretch. What kind of number would this coefficient needed to be if we were going to do a vertical compress?
1/4.
Like maybe 1/4, a fraction between 0 and 1. Excellent. Okay, there's our vertical stretch. So this is the graph of y equals 4x squared. Okay. Now we're going to do a vertical shift up of 5. So now we're going to go up 5. That's a shift up of 5. It's not a factor of 5, but we're just going up 5. We're adding 5 to it, correct?
Yes.
So we're just going to add 5 to each y value in the red. Forgot to label that one. This is negative 1, 4. So we'll add 5 to that. Okay, so now we'll have 0, 5. 0, 5. We added 5 to the y values. 4 plus 5 is 9, so now we have 1, 9. And we have negative 1, 9. So now it's the same old graph, it's just been shifted up, 5. Everybody good? And I'm looking for an interesting color. Oh, here's green. Okay, so now we're going to take this and move over to the right 9. Now, horizontal makes you think what values? Axis. And we're just shifting to the right 9. We're not doing a factor of 9. We're just shifting to the right 9. So we're going to add 9 to each of our x values. Okay? So that will take me at, I'm going to move over 9, just showing you where I'm going here. So now we have the point 9, 5. We're going over 9 to 1, so that would be 10, 9. 10, 9. And we're adding 9 plus negative 1 is 8. So we now have 8, 9. Oops. About to miss my dot here. Make that really thick. Okay. So there's our graph. All right. Now you're in the middle of a test. How are you going to double check that just to be sure?
Do it again.
Do it again. How about just substituting some numbers in? Let's put in a 10. 10 minus 9 is 1. 1 squared is 1. 4 plus 5 is 9. So there's your point. If x is 9, 9 minus 9 is 0. 0 plus 5. And the same deal with 8. If you square a negative 1, that's positive 1, and you're at 9. Okay, so we know we're good. All right. Now, I'm not sure if I mentioned this yesterday, that when you have your equation for your function written in the form a times x minus h squared plus k, one nice thing about that is you immediately know what the vertex is. In general, what's the numbers for the vertex here? Compare that to the problem we just did. Do you see what the vertex is by looking at it in that form? What is it? HK. So if you have your function written like this, you immediately know the vertex is going to be HK. You immediately know the A's, and when the A is positive, you know your graph's going to go up. When the A is negative, you immediately know it's going to go down. Okay, so really, if you have it in this form, you almost could start at your vertex, because there's your shifts, and then just worry about the vertical stretch. So you could almost leave out on the last two steps. Just get there and then do your stretching. All right. Does this function have a maximum or minimum value? Minimum. Question is, what is the minimum value of the function?
5.
Everybody tell me?
5.
5. Okay, value of the function means the y value. Okay, what is the domain for this function? What's the domain for this function? Domain.
8 to 10.
-1.
Go back to your graph. How do you determine what the domain of a function is?
What?
All the
One equals
possible
zero.
x values.
Yeah, you're looking to see if you plug, is there a value for x, if you plug it in, it's going to make the y undefined, right?
Yeah.
Can you put in any value for x you want?
Yeah.
Sure, your domain is going to be all real numbers. This graph just goes on forever and ever, so eventually it's covering all your x values. So your domain is x is all reals. That's a little symbol just saying all reals. Or if you wanted to put it in interval notation, it would be negative infinity to positive infinity. All reals. Okay, what about your range? What are you thinking of when you hear the word range? Y values. All right, so you come over here and you see what y values are covered. What's your range?
5 to 10.
Okay, and if we put in interval notation, that's a square bracket, 5 to infinity. Okay. How about the interval where the function increases? When you're defining a function where the function increases or decreasing, it really means over what domain. You're always working on domain. So over what open interval is this function increasing?
9 to infinity.
9 to infinity. Over what open interval is it decreasing?
Negative infinity.
Negative infinity to 9. Is there anything else I forgot to ask? What's the axis of symmetry? Axis of symmetry. What's the equation? It's a line that goes right through the
X equals 9.
X equals 9.
x equals 9 is your axis of symmetry. The nice thing about axis of symmetry is if you know a point, say to the right, if you knew the point, then you could go the same number of units to the left and you'd have the same y value. So the axis of symmetry often helps you find other points real fast. All right. Did I leave anything out? I think that's it, don't you? All right. Now let's look at it in the form y equals ax squared plus bx plus c, which is the method that we're looking at in section 3.1. And you've already told me that if a is positive, it opens up. Some of the things we want to do are the domain. We already know that. That's pretty easy. We need to know, does it open up or down? How do you easily find the y-intercept? This is when it's written in this form, you always want to know what the y-intercept is. If you let x equal 0, what's the y-intercept going to always come out to be?
C.
C. Okay, how do you find your x-intercept,
Put it in the quadratic form.
if any? All right, that's where you let y equal 0. So you'd have 0 equals ax squared plus bx plus c. And you either factor, remember, or you guys are going into the quadratic formula. Okay, to solve. Now, we don't always have x-intercepts, do we? If you have the graph of y equals x squared plus 4, that's the good old graph y equals x squared, but shifted up 4. So there are no x-intercepts. All right, but let's pretend that we didn't know that. And we were going to solve for x-intercepts. You would have 0 equals x squared plus 4. X squared equals negative 4. What's the next step? Square root both sides. So you got plus or minus the square root of negative 4. So when you get a negative underneath the radical, there are no real solutions. This is the real number coordinate system. So there are no real solutions here. So therefore no x-intercepts. You do have complex solutions, but not real. Did you have a question?
I was just going to ask if there will always be complex zeros if there isn't a real zero.
That is an excellent question. If there's not a real zero, and you know that we can talk like square root of 2 is a real number, okay? If there are no real zeros, then and it's a quadratic, you would have 2 complex zeros. Okay? Good question. All right, everybody good with that? All right, does anybody, not anybody, who will be first to remind me from the olden days what term is used to describe b squared minus 4ac? Starts with a D. Yeah, discriminant. And your book talks about this, discriminant. And the deal is that if the b squared minus 4ac comes out to be a number that's a perfect square, like 4, 9, 16, 36, perfect square, then you know your x-intercepts are going to be nice rational numbers. But if your b squared minus 4ac comes out to be something like 37, something you can't take the square root of, then you're going to have real number solutions. You know, the square root of 37, the decimal doesn't repeat. So you're going to have to just get an approximation there. I mean, those are real values, but you wouldn't be able to exactly find the spot on the number line. And then, of course, if you're b squared minus 4ac, which was what would happen right here with the x squared plus 4, that's negative, then you have no real solutions. Okay? Everybody good? Let's take an example. And I decided let's go right to the book so that we can see some of these problems worked as motivation. Page 312. Page 312 in the textbook. And I'm going to pick problem number 48 because I thought that looked probably ugly. Trying to pick some of the uglier ones to do. This is page 312, number 48. It's the f of x equals minus 3x squared plus 3x minus 2. And the instructions are we want to graph this function. We want to determine if the graph opens up or down. We want to find its vertex, axis of symmetry, y-intercept, and x-intercept, if any. State the domain range. Where's the increase, decrease? And then it says verify it using a graphing utility. The nice thing about having a graphing calculator is that you can just double check your work. Again, your test is no calculator. Okay, so be sure that you're learning to do all this. All right, I'm going to get you to help me and tell me every step of the way. I hope. All right, this is page 312, number 48, and it's f of x equals negative 3x squared plus 3x minus 2. All right, so you were given this problem on a test. I'm just going to have you tell me some things. What's one thing you notice right away?
Basic function.
It's a basic quadratic, y equals ax squared plus bx plus c. So you already know it's the graph of a parabola. All right, that is excellent because you want to start looking at functions or equations and have a good idea what they look like, and you knew that. Excellent. Okay, what's the next thing you notice?
It opens down.
Okay, it's going to, your a, which is equal to negative 3, and since that's less than 0, we already know that the parabola is going to open down. So does that mean I'm going to have a max or a min value?
Max.
I'm going to have a maximum value at the vertex. Okay, what else do you know? Or are you going to figure out?
It doesn't have rational zero.
Excuse me?
It doesn't factor.
It doesn't factor? Okay. So you're talking in terms of an x-intercept?
Yeah.
Okay, so the next place you wanted to go was intercepts. All right, the y-intercept is going to be easy.
Negative 2.
If x is 0, y is negative 2. All right, I'm going to work on sketching the graph at the same time. So go ahead and draw your coordinate system. Remember, this is the real number coordinate system. Since I have a y-intercept of -2, I'm guessing that I've got some smaller values here. Okay. All right, tell me a y-intercept of -2. All right. Everybody good? Okay, for the x-intercept, remember we let y equals 0 and solve for x. So we have 0 equals minus 3x squared plus 3x minus 2. That might factor, by the way.
I don't think it does.
I think it does, but we'll jump right. For me, and probably for you, if you don't see right away how to factor something, I would jump in the quadratic formula without spinning your wheels. All right, so we're going to, I think it factors, but we'll jump into the quadratic formula. X equals, what's the first term?
Minus b.
Okay.
3x.
-3, the coefficients. Remember, it's x equals -b plus or minus square root b squared minus 4ac. Remember that square root's all over that whole part, and then the entire thing is multiplied by 2a. Be sure you memorize this. One way, shape, or form, it's going to be on a test or a final exam. That's one of those basics that you got to know to get out of here.
So do we write 3x squared underneath there? Under the square root, do we write 3x squared or we just write 3 squared?
These are coefficients. When your equation is ax squared plus bx plus c, the a is -3, the b is +3, and the c is -2. Okay? That was a good question because some people get that confused. Are you good? Okay. So in my problem, the a is -3, the b is +3. So we got to do minus b. So if b is 3, minus b is -3. Plus or minus square root of b squared, which is 3 squared minus 4, and the a is -3, and the c is -2. All over 2 times -3. Does everybody see the a's, b's, and c's? Okay, so we have -3 plus or minus the square root of 3 squared is 9. You're right. It might not have factored. You had great insight there. I was looking at those and I was thinking there must be a 6 in here. Yep, that's going to work. You're right, it didn't work. 3 squared is 9. All right, -4 times -3 is +12. 12 times -2 minus 24. All over 2 times -3, which is -6. And we get -3 plus or minus the square root of 9 from that must be about a -15. And do I need to go any further? No. There are no real values for x. No real values for x. So therefore, this graph is not going to cross the x-axis or touch the x-axis. Okay? So no x-intercepts.
Did we already do the step where we had the vertex?
No, he led me in the direction of intercepts first. Now we'll go back and do vertex. Okay? All right. Are we good, everybody? No x-intercepts? All right, so now you want to do the vertex step. Okay. All right, the formula for vertex x is what? Negative b over 2a, which you notice is the first little term in the quadratic formula. All right, so negative b is going to be that minus 3 over 2 times negative 3, which is negative 3 over negative 6, or positive 1/2. So the x-coordinate of the vertex is positive 1/2. How do I find the y-coordinate now? All right, so the y, which is f of x, and I know what the x value is, so I'm going to evaluate the value of the function at 1/2. So it's minus 3 times 1/2 squared plus 3 times 1/2 minus 2. Okay, looks like I need to flip to the next page. I'll rewrite that. Y equals minus 3 times 1/2 squared plus 3 times 1/2 minus 2. All right, so that's negative 3 times 1/2 squared is 1/4 plus 3 times 1/2. We know that's 3/2 minus 2. All right, negative 3/4 plus 3/2 minus 2. All right, how do you add these fractions?
Okay, where are you plugging the halves of that?
Into my function. I'm solving for y when
Okay.
x is 1/2.
Okay.
Okay? Is that good? I'm glad you're asking these, because if I lose you in here, I'm sure I'm losing everybody that's watching this by video. So don't keep me posted when I'm going too fast. All right. What do we need to do to add fractions here? Good old common denominator. What's my common denominator for all three of those terms? 4. So we have negative 3/4. And what's 3/2 with the common denominator 4? Okay, remember you're just multiplying the 3/2 by 2 over 2. So we get 6/4 minus. And then same deal here, we'll multiply this 2, you might write that as a fraction, 2 over 2. So 2 is the same thing. Oops, how about 4? I need a common denominator, 4. And that would be 8/4. We know 8/4 reduces to 2, correct? All right, so we have common denominators, so we'll just add across the top. Negative 3 plus 6 is 3. 3 minus 8 is negative 5. Negative 5/4?
Yeah.
Okay. So my vertex then is the ordered pair 1/2, negative 5/4.
And see, I had did the vertex before I did the intercepts, so I already, I didn't have to do all the math for the intercepts because I already knew I wasn't going to have any.
That was perfect. Okay, in case you didn't hear her, she said that because she knew the parabola was going to open down, the first thing she did was do the vertex, and because she saw where her vertex was, and it was opening down, she knew there was no need to worry about x-intercepts. That's absolutely perfect and fine to do. Okay? All right, thanks for making that comment. Everybody good? Okay, so let's go over to our graph and plot our vertex. 1/2, negative 5/4. 1/2 is along here. Negative 5/4 is like negative 1 1/4. So the vertex is at 1/2, negative 5/4. Okay? So this part of the curve we already know. All right, and I'm going to put in my little axis of symmetry here. I wanted to do that in red. Where's my red pen? Here it is, red. Put put in the axis of symmetry coming in. What's the equation for this again? X equals a half. Okay, so I know that when I went a half a unit to the left, the y value was -2. Somebody tell me another point right away. One. If I go a half a unit to the left, the y value is -2. A half a unit to the right, the y value is also -2 because it's symmetric. So you'll have the point 1, -2 on your graph. Okay, this distance right here is a half. So this way is a half. That's why those little y-intercepts are so nice to have, because it helps you find another point on the graph really fast. Okay? Everybody good? All right, so my vertex is 1/2 -5/4. What is my domain here? Say it. Domain. Tell your neighbor. Tell your neighbor. What's the domain?
The half.
Domain goes with x's or y's?
X's.
X's. What x's are covered here?
All the numbers.
All real numbers. Domain's all real. What's my range?
-5/4 to -infinity.
Okay, the y values, the biggest y value is -5/4. Range is y values. Okay, what is the maximum value of this function? -5/4. Maximum value of the function, -5/4. Did I leave out anything?
Why would the range be -5/4?
The range is -5/4 is the, oops, goes this way. The range is what y values are covered, and you always put your smallest value first, so it's going from -infinity to -5/4. Or you might write y is less than or equal to -5/4 is your range. -5/4 is your biggest y value, and it goes down.
I thought you said -5/4 to -infinity.
I meant to say -infinity up. Well, that's a parenthesis.
Yeah.
-infinity up to -5/4, and that's a square bracket.
And you said your range is always from your lowest y value to your highest y value?
Right. Yeah, when you're putting in interval notation, you go from low number to high.
What's the total?
Okay. All right. Thank you. You straightened me out. Everybody good? All righty. We are experts on that, aren't we? Let's look at a couple other problems right from the textbook. I'm on page 54. No, I'm on page 313, problem number 54. I'm on page 313, and we're going to look at problem number 54. Can you see that? Page 313, problem number 54. Determine the quadratic function whose graph is given. They're wanting you to come up with the formula for this function. All right, talk it out with your neighbor. You want the equation for this function.
Why would this vertex yeah, when the vertex was
Alright, the last
we
one.
moved one to opposite. So that was -2.
Number
The vertex is 2, 1.
Isn't that the x-intercept?
It should be less than it should be 2. Like y plus 2 is 2.
2 to the left, and then
I mean, no, 1 plus 1.
I'm guessing
1 to the, no, it's 1 to the right, and then 1 up, and the right one up. So it's 1.
No, but it wants the quadratic. not transformation.
How's your neighbor doing? You have confidence in your neighbor? Well, Robert over here has no neighbor. These ladies will let you talk to them. Okay, we're on page 313, number 54. And you notice that this is a parabola that opens up. What else did you notice? The vertex is 2, 1. And you have a y-intercept. Ordered pair 0, 5. Okay. All right, you've got two forms that you've studied for the graph of for the function parabola. Y equals a times x minus h squared plus k, or y equals ax squared plus bx plus c. All right, let's just get a show of hands here. How many want to jump on the transformation formula? Is that a hand up, or is that just a stretch? Sort of hand up. How many want to jump on this one? 2 of you?
Wouldn't that be more work?
Yeah, I think the first one would be easier.
First one's easier, right?
Why do you
Because
think
we
the
have
first one's easier?
We have our vertex.
Because you
Okay.
don't have
You already
to
know
solve for
vertex.
Right. I believe the first one's going to be a little easier because you've already learned in this form that the ordered pair HK is the vertex. And so you already know 2 of the unknowns right away. If you come over here, I think it's going to be a little bit more work because you're going to have to remember the 2 came from being negative b over 2a. So you're going to have a little bit more effort to put out. All right, so let's go with what we know. Y equals a times, what goes inside parentheses here? X minus 2 squared plus 1. Okay, so far we used our vertex. Okay. All right, how in the world do you think we're going to come up with what A is? If you know a point here, that's an x and a y value. If I substitute that in, won't that give me everything but A?
Yeah.
All right, so when x is 0, y is 5. So I'm going to use the point 0, 5. Y is 5 when x is 0. And that's going to give me an equation in one unknown, so I can easily find what the A is. So 5 equals negative 2 squared is positive 4. 4a plus 1. So now we'll subtract 1 from both sides, and we get 4 is equal to 4a. Divide both sides by 4. A is going to be equal to 1. So my equation should be 1 times x minus 2 squared plus 1. Let's just double check that and make sure. When x is 0, negative 2 squared is 4. 4 plus 1 is 5. So you know you have the point 0, 5 on there. Your vertex is 2, 1. Looks like we have a perfect equation here. And if you wanted to put it now in the form ax squared plus bx plus c, I think you could pretty easily just by squaring this. And you'd be fine. This is perfectly great form, so I'd stop right there unless you had to do otherwise. Everybody good? It's not as bad as it looked, is it? Okay, next example we want to look at is number 74 in the exercises. So this is on page 314, number 74. And as soon as you see the heading on this question, you know why I pulled it up. Okay, see that good old term you're going to look at a whole lot in calculus, the demand equation. We're on page 314, number 74. the price P in dollars and the quantity X sold of a certain product have this demand equation. So that's what the price is based on. Okay? And again, this basically is if somebody's buying in bulk. The more you buy, it's going to reduce the price. See that negative 1/3 X? So the price of the item is basically $100 as long as you're buying between 0 and 300. And then the more you buy, you start getting a little bit off. All right. The first question, express the revenue as a function of X. All right, tell your neighbor right away how to do that. Express the revenue function as a function of X.
Yeah.
All right, in general, what is revenue? All right, R of X, page 314, number 74. Okay, we need to zoom out. There we go. Thank you. We have that the price is negative 1/3 X plus 100. And part A says, what is revenue? In general, revenue is...
Price times number of items.
Yeah.
I love how you said it with confidence. Thank you very much. It is the price times X. Okay, and let's make that substitution what P is. So that's negative 1/3 X plus 100 times X. I just made the substitution for what the price is right here. Okay, and let's multiply that out. That's negative 1/3 X squared plus 100X is my revenue function. So based on the number of items that are sold, X, this would be the revenue I'd have coming in that day. So this is part A. Revenue is written in terms of the number of items sold. Everybody good for A? Let's go to B. What is the revenue if 100 units are sold? What is the revenue if 100 units are sold? How do you figure that one?
Our X is now 100.
Okay, you're going to find the value of the revenue when X is 100. Isn't that what you said? So it's negative 1/3 times 100 squared plus 100 times 100. And let's see what we get when we do this. 100 squared. We could do some factoring here, but we're not going to do that. That's negative 333.33. That 3 is repeating. Plus 1, 2, 3, 4 zeros and a 1. 10,000. 100 times 100 is 10,000. Okay. And punching away on our calculator, this comes out to be $9,666.67 approximately.
9,000.
Excuse me?
Wouldn't it be
Yes,
Whoops, did I do it wrong?
6,000.
Oh man, I put 100,000 in my calculator. Wrong. See, you should have a little common sense here, which I didn't have. Okay, how about $6,666.67? I did this only because I was checking to see if you guys were still with me. Okay.
Sure.
Thank you very much. Don't ever let me do something wrong. I appreciate it. Everybody good? Okay, let's go to part C. So that says when you sell 100 of these items, your revenue is $6,666.67. Okay, C. What quantity X, what value of X maximizes the revenue? What's this the graph of right here, if you were going to graph it? Parabola, open up or down? Down. So you got a parabola that's going to open like this. How are you going to find where that max is?
Yeah, opposite of B.
Yeah, get your vertex,
Yeah.
right? So for part C, it says because your formula is going to be X, and this is revenue when you graph it. So X is negative B over 2A. Your B is 100. 2 times negative 1/3. Okay, I'm just solving this equation for the x coordinate of the vertex. And so we'll have 100 divided by, 2/3? And that's 150. Because what happens is you have 2/3, you invert and multiply. So it's 100 times 3/2, 150. So the x-coordinate's 150 whenever you maximize your revenue. So the question is, what quantity x maximizes the revenue? So when I sell 150 items, I'm going to have a maximum revenue. Is that good so far? The next part of the question says, and what is the maximum revenue? So you have to evaluate revenue at 150. So we have negative 1/3 times 150 squared plus 100 times 150. Am I running off the sheet? There we go. So that's 150 squared. Negative 1/3 times 22,500. And then I should have gone on another sheet of paper. Let me rewrite this. I see I'm about to run out of time, right? R times 150, negative 1/3 times 22,500 plus 100 times 150, 1, 2, 3 zeros, and a 15. Okay, so let's see what this is. This is negative 7,500 plus 15,000, and that's probably 7,500. Is that correct? That sounds right. So the revenue, when you've done 150, the maximum revenue is going to be $7,500. Everybody good with C? All right, last little part, D. What price? What is P when you charge your maximum revenue? What are you going to do, everybody? How are you going to find that what that price is to get your maximum revenue? Here's your price function, right?
Plug in.
And so we're going to put in the place of X, what, 150? So we have price equals negative 1/3 X plus 100. So negative 1/3, and in the place of X we have 7,500 plus 100. 7,500 divided by 3 will make that negative. Whoa. Did I do some numbers wrong somewhere?
Unless you put it 2.5.
Negative 1/3 X plus 100. What was I thinking here? I went into a different formula. It's not, that's not X. What is X? X is 150.
Yeah.
Very important we get the right numbers in. All right, 150 divided by 3. That's 50, of course. Negative 50 plus 100, $50.
I was like, that's not a nice number.
Excuse me?
I was like, that's not a nice number.
Yeah, it was not about to be a nice number. Be sure you put in the right variables there. Everybody doing well? Seem pretty easy? Alrighty, we're going to stop there, and then when we come back, we're going to work on areas bounded by curves. Okay. curves.
So there's no,
Alrighty, go ahead. Yes.
there's no calculators on the test?
No what?
Calculators?
No the test is no calculators.
What about like regular, not reference
Simple four
calculators?
No calculators of any kind.
Not even for like the revenue stuff and all that.
The numbers will be good enough
That'll
that
be easy.
right. The numbers will be easy enough. Or if you get something like 17 over 3, just leave it. I'm not asking you to convert to decimals or anything. Okay, I'm more interested in the process, and then you can leave your answers exact. All right, we're now at lecture 6B, and we were having some questions because at the end of 6B, we should be through covering all the material that's on test 1. The very last topic on that we're covering is called regions bounded by curves. And we're going to flip over to chapter 5, section 1 to remind you about solving equations by the method of substitution. And for NC State, we assume that this is kind of something you already know how to do. For this particular class that's in here, be sure you have questions organized for the next lecture, specific questions of anything we've covered, know what your question is, and then all these people that are watching this by video will be so happy that you ask these questions. All right, hopefully before you started this lecture today, you got this sheet, and did y'all see that light blinking up there? Okay, you got this sheet and you practiced solving, graphing these equations, so that'll go pretty quickly today, I hope. All right, so what's going to happen in calculus is that you're going to have some functions, and when you graph them on the same coordinate system, they're going to form a region. And what we need to do is be able to identify the region, and then we want to algebraically be able to go and find the points of intersections of the curves. And that's very necessary for being able to use the calculus concept integration to actually find the area of that bounded region. So the first place we're going to focus on is over in chapter 5, and I'm on page 506. Page 506. And we're going to be focused on, this is just straight lines, but they don't have to be straight lines, but where there's an intersection of two curves, where there will be a point of intersection. And you'll notice that when two curves, and again, I know these are lines, but where two curves intersect, they're going to have to share a common point, x, y. That's their point of intersection. And so how do we find where those two curves intersect? All right, the method that we're going to use in this class, especially since everything's not linear, is from our objective 1 in this part, solving systems of equations by substitution. Solving systems of equations by substitution. And I'm just going to sort of quickly talk through this example 4 to tell you what happened here. You had two curves, and these two curves happen to be straight lines. Well, we said that where the two curves intersect, they have to share a common point, xy, if they intersect. So in this particular problem, they start out and go, okay, well, let's solve the first equation for y. And then if I take this equation for y and replace it into the second equation, then I'll have the second equation only in terms of x. So we've been doing substitution all along, really. So they just took the first equation, solved for y, and substituted it into the second equation. So then you have an equation only in terms of one variable, and you just follow it down. So you got your x, and then of course once you know your x, you can put back into either equation to get your y value, because they both have to be the same thing for the same y. They both have the same point x and the same point y. So all we're going to do is take one equation and substitute into the other. Okay? Substitution. There's, on page 508, some little steps. Pick one of the equations and solve for one of the variables in terms of the other. Substitute into the other equation and have fun. That's what steps 3, 4, and 5 say. Have fun solving. All right. So it sounds worse than what it really is. All right, so we're going to take this sheet, and I had asked you ahead of time to sketch some graphs, and let's find some points of intersection. All right, so I would like to take from you guys some particular problems on here you definitely want to let's see work today, based on your graphs that you've already done. Give me some numbers of these problems that you definitely want to see done today. Number 3, that's a very good one. Another one.
5.
Number 5, that's a very good one. I'm glad you picked that.
8.
Number 8, okay.
2.
Number 2,
4.
1, 2, 4, 6, 7, 9, and 10, okay.
3 was part of it too.
Just do all.
Okay.
Just do them all.
All right. Let's don't do them all. I just want to make sure I got everything covered. This has y equals 0, x equals 1, x equals 3. That's very similar to these where it has y equals 5 and x equals 0. So those are just those lines. So I think we're good there.
About 4.
Number 4. Okay, we can do number 4. Those are just quadratics. All right, let's see how we've done after this. Actually, I'm going to pick number 1 to get us going. I'll pick number 1 to get us going. Alrighty. And I need your help on these. Alright, let's set up our coordinate system. Okay, this kind of question is always, these problems are always on your test, always on your final exam. Very, very important pre-calculus concept. So usually worth about 10 points. So do not ignore.
And this is number 1.
We're going to do number 1 first. Yep. We're going to graph y equals x squared minus 1 in blue. And we're going to graph y equals x plus 1 in red. Okay, so the first part of the instructions is to sketch the curves. All right, the first thing you saw was y equals x squared minus 1, and everybody said that's the graph of a parabola. It's that good old x squared, and what happened to it?
Move to the right.
Whoa.
Oh.
Shift down.
Down 1. It's a vertical shift down 1. So we have over 1, up 1, and here's the graph very quickly of good old y equals x squared minus 1. Okay? All right, in unison. Y equals x plus 1. What's that the graph of?
A line.
A straight line. The y-intercept is?
1.
1. The slope is?
1.
1. So we'll go up 1 over 1. Up 1 over 1. Whoops. All right. Down 1 over negative 1. Not exactly sure, based on my crude sketch here, where these points of intersection is. All right. This is in red, we have the line y equals x plus 1. All right. Bounded region means it's covered, enclosed by these curves. Does everybody see that this is my bounded region?
Why is that?
The bounded region, it says shade the bounded region. Bounded region means it's enclosed by the blue and the red. The red and the blue enclose it. Okay. Now we have to find where these two curves intersect. And this part looks okay over here. My graph is not perfect over here, but we got the idea what it looks like. But we're going to use the method of substitution to help find where these curves intersect. All right, so I have two equations. I know that y is equal to x squared minus 1. Y is also equal to x plus 1. We're going to substitute one curve into the other. This is so nice, it's already set up for us. If y is equal to x squared minus 1, can I just come down here and substitute it for y?
Yeah.
I'm going to substitute one function into the other. Some people like to say, okay, y has to be equal to y. One y is x squared minus 1, the other y is x plus 1. So it depends on how you like to say it. Or you're just taking one function and putting into the other. So you're replacing the y here with the x squared minus 1. Is that good? All right. As soon as you see x squared minus 1 equals x plus 1, your brain starts thinking quadratic equation because I see an x squared in there. So let's get all terms on the same side. X squared minus x minus 2 equals 0. Okay, I notice that's going to be a quadratic equation because it's got an x squared in it. So I subtracted x from both sides, and I subtracted 1 from both sides. Everybody good? And then it's, yeah.
So hold on, you said x squared minus 1 equals x squared plus 1. And then you subtracted x squared from both sides, you said?
No, I subtracted x from both sides.
Okay.
And I subtracted 1 from both sides.
Okay.
Okay? Everybody good? All right, now you've got this quadratic equation set equal to 0. What's the two methods we usually go through for solving those? Factoring or quadratic formula. And fortunately, this one factors pretty easily. That would be x minus 2x plus 1. Looks like my graph's off a little bit here. Way off. All right, so setting each factor equal to 0. Oh, should be over here. There we go. Ignore all that. X equal to 2. X equal negative 1 when I set each factor equal to 0. All right. Now, if x is equal to 2, how do I find the y value of this point of intersection? Where do I put this 2?
Into the original formula.
Into either of these original, because they both have to have the same y. If I put a 2 in here, 2 squared is 4. 4 minus 1 is 3. If I put it in the other one, 2 plus 1 is 3. So this point of intersection is 2, 3. And then if I put negative 1 in, we already saw it look like a 0. Negative 1 squared is positive 1. 1 minus 1 is 0. Or if we put negative 1 plus 1, the y value is 0. So our 2 points of intersection of the bounded region is negative 1, 0 and 2, 3. Ask your neighbor if they followed all that.
Okay. The last part. Okay, why did you plug the 2 in the top? Why did you put x minus 2?
Okay. You mean when I was working with x equals negative 1?
Uh-huh.
Okay, I'm looking for the point of intersection here. I knew x was negative 1, and they both have to have the same y value.
Mm-hmm.
So I can plug it into either one, and I usually plug it into both just as a check.
Okay.
So negative 1 squared is positive 1, 1 minus 1 is 0, as well as if I put in the next one, negative 1 plus 1 is also 0. Everybody good? Okay, let's have fun with number 3. So did we do everything? Yep, we sketched the curves, we shaded the bounded region, and we identified the points of intersection of these two curves, called vertices.
So, to identify the vertices, you just gotta set them equal to each other?
Yep, you set the y's equal to the y's.
That's it?
Excuse me?
That's it?
Yeah, it sounds too easy, doesn't it? Alrighty, let's go to problem number 3 at your request. Number 3. X squared equals 4 plus y, and x squared plus y equals 6. Okay, as soon as you saw x squared equals 4 plus y, what'd you know this was going to be the graph of? A parabola. And you probably rather look at it as y equals x squared minus 4. That's a little bit easier to know right away what the graph is. Write it as y equals. All right, tell me, y equals x squared minus 4 is the graph of parabola, and what are you going to do to it?
Vertical shift up.
It's
Down.
down to negative 4. So it's going to go over 1, up 1, over 1, up 1, over 2, up 4. So my graph looks like this. The x-intercepts are 2 and negative 2. You can see that pretty fast. X plus 2, x minus 2. Okay. Alrighty. What about x squared plus y equals 6? You recognize that right away as the graph of a parabola. So let's write that as y equals minus x squared plus 6. Okay, let's analyze this. It's going to be the graph of x squared. But what does that minus do? Flips it down. So it's going to go down. And then this plus 6 tells you then shift it up 6. So we're going to be right here at the 6. And then we're just going to graph good old y equals negative x squared. So we'll come over negative x squared. And if I go over 2, I would come down 4. 1, 2, 3, 4. And come over 2, down 4. 1, 2, 3, 4. Okay. All right. Basically, I was just graphing y equals negative x squared, and I just went over 2 and down 4, and over 2, down 4. Okay? Over 1, down 1, over 1, down 1, over 2, since it's negative, over 2, down 4, over 2, down 4, like the 0.24. Okay, everybody see the bounded region? Of course you do. All that's enclosed between the green and the red. All right, but we need to find out where these two curves intersect. All right, so we know that y is x squared minus 4 and y is minus x squared plus 6. So how do we go about this algebraically?
Set them equal to each other.
Set the two curves equal to each other. I always say I'm going to set the y's equal to the y's. X squared minus 4 equals negative x squared plus 6. Oops. What's my next step?
Put them on the same side.
Get everything on the same side. So I'm going to add x squared to both sides. And I'm going to subtract 6 from both sides. I'm going to add x squared, and I'm going to subtract 6. So I get 0 equals 2x squared minus 10. How are you going to solve this?
Put the 10 on
quadratic.
You can put it in the quadratic function, and that is perfectly great to do. But I just want to remind you, you have a square root principle that says if a squared is equal to b, then a is equal to plus or minus the square root of b. That's a square root principle from the chapter review or chapter 1. So in this case, since you only have x squared and there's no other x in there, it might be easier to go with the square root principle, which would be 2x squared equals 10, x squared equals 5. This is called square root principle. Okay, it's one of your little rules. And so now it says, let's take the square root of both sides plus minus. So x then is equal to positive square root of 5 and negative square root of 5. And that's the same thing you would have gotten had you gone with the quadratic formula up here.
Okay.
Because your b is a 0. Okay. All right, so over here, this is going to be a square root of 5, and we got to find the y value. And over here, this is a negative square root of 5. By the way, square root of 5 is about what number without punching away on your calculator?
2.0.
It's pretty close to 2 because the square root of 4 is 2, so square root of 5 is 2.1 or 2, because the next one would be square root of 9, which is 3. Okay, so if x is square root of 5, how do I find out what y is?
Substitute.
Yep, let's just go right up here. Square root of 5, and we're going to square it minus 4 is equal to y. What's the square root of 5 squared? 5. 5 minus 4 is the y, so y is equal to 1. So y value is 1. By the way, you already know the y value over here because these are both symmetric about the y-axis. But if you didn't, what happens if you square a negative square root of 5? You still get 5, right? Negative square root of 5 times negative square root of 5 is positive 5. 5 minus 4 is 1. You can do the same thing over here. This would be minus a square root of 5 squared plus 6. Remember, without parentheses, it's only the x that's squared and then the minus. Pointed that out a couple times. Be really careful. So the square root of 5 squared is 5. Negative 5 plus 6 is 1. So there's your 2 points. Who has a question for me? Anybody? Is it looking easy? Answer that's yes. I think I'm going to skip number 4 because that looks like the same kind of problem. You asked for it, but I think you're okay. 6x minus x, you know that's the graph of a parabola. Y equals x squared, that's a parabola that's going to open down. And y equals x squared minus 2x, that's also the graph of a parabola that is going to open up. Okay, so number 4 is just the same kind of problem where you're going to graph parabolas. Okay, let's go to problem number 5. Try number 4. If you have questions tomorrow, we'll go through it. Okay, number 5. Y equals x to the 4th, and y equals x squared. Okay, what's new here is we haven't looked at the graph of y equals x to the 4th before. But we do know all about y equals x squared. Okay, in this particular problem, I really want you to spread your units out on the x-axis. And on the y-axis. Okay. All right, so let's graph y equals x squared. That's easy. 0, 0, 1, 1, negative 1, 1. And the graph looks like this. Oops. Y equals x squared. Okay, and let's just put in when x is equal to a half. There's a half in here. When x is equal to a half, what's the y value?
1.
1 half squared is 1 half times a half. 1 half times a half.
Oh, quarter.
Fourth. 1/4. Okay. All right, that's just another little point on the graph. All right. Now what about y equals x to the 4th? Let's do that in green. Let's just plot some points because we haven't really looked at that. X, and y. And we'll put in -1, 0, 1 to get us going. What's -1 to the 4th equal to? -1 raised to the 4th is positive 1. 0 raised to the 4th is 0. 1 raised to the 4th is 1. So when I get ready to graph this, it looks like it's the same old points, doesn't it?
Yep.
All right, when it looks like that, then you got to go, well, something must be going on between, say, -1 and 1. So let's just pick x equal to 1/2. What is 1/2 raised to the 4th? 1/2 times 1/2 times 1/2 times 1/2? 1/16. Okay, so when x is equal to 1/2, the y value is going to be 1/16 down here. Same thing with -1/2 is going to be at 1/16. So what's going to happen is this curve is going to come underneath the blue one until you hit 1. And then, of course, you know when you raise something to the 4th, it's going to fly off really fast. So the graph is going to come under here like this and then fly off. This is the place, of course, to look for this is after 1, so you know it flies off. For example, if x is 2, the y value is 16, whereas on y equals x squared, when x is equal to 2, the y value is equal to 4. So after 1, x to the 4th goes up really fast, while y equals x squared doesn't go up quite as fast. Okay, so any of these curves you start to sketch, if they look like they're on top of each other, and that usually happens between -1 and 1, you want to spread out your units. Yeah?
Oh, like, theoretically, couldn't, like, an x to the 4th graph, like, have more than one region?
If more than one, say it again.
Like,
Because you're going to say it's going to turn and come back. Yeah, if it's got some more terms with it, this is actually called a power function. A power function where it's just an x to the 4th, but if it had some other terms, it could have 4 zeros, meaning that it could touch the x-axis 4 times if it had some other terms with it.
but like, if it crossed over that parabola more than once.
If it had some more terms, but not for our little power functions, yes, it could, depending on what your function is. These were carefully selected for this exercise. All right, does everybody see the bounded region? And we can see what those points of intersection are, but we're going to pretend that we couldn't. So we're going to solve it algebraically. What do you do to solve this one algebraically? Set them equal to each other. So the y is equal to the y. Your test question says solve for the points of intersection algebraically. That means don't just read them off the graph. All right, so we have x to the 4th equals x squared. What's my next step? Everybody tell me. Okay, get all the terms on one side. X to the 4th minus x squared equals 0. I'm solving for x. What's the next thing you would do here?
You add the
Can you factor out in it?
Big F word, factor, right. Common factors here. X squared times x squared minus 1. Factored out of x squared using that distributive property in reverse. What do you notice about x squared minus 1? How does that factor? Difference of two squares. So you got an x squared times x plus 1, x minus 1. That's the difference of two squares. Or you could go in with your square root principle there and get that. All right, so I've got 3 factors multiplied together to set equal to 0. So x squared equals 0, x plus 1 equals 0, and x minus 1 equals 0. So x squared equals 0 tells us, we're going backwards on the paper here, x equal to 0, which is this value. X plus 1 equal to 0 tells us x is -1, which is right here. And x minus 1 equals 0 tells us x equal to 1, which is right here. exactly what we already knew so far. Okay? And now the y values are going to be very easy to find because 1 to the 4th is 1, and 0 squared is 0, and negative 1 squared is positive 1. And there's our 3 points of intersection. How's that? Good? Everybody good? Question? Did you follow all this? Was this too fast for anybody? Okay, let's look at number 8. Number 8. Number 8. We have y equal to 5, y equal to the square root of x, and x equal to 0. Okay, got all my colors lined up. Remind me what the graph of y equals 5 looks like. Yes, you're so good. Y equal 5 is a horizontal line because every point on this line has a y value equal to 5. Okay, I'm going to jump on x equals 0 next. X equals 0 is the vertical line, the y-axis. This is my y equal to, x equal to 0. Every point on the y-axis has an x value equal to 0. Okay? All right, with our Sesame Street, remind me what y equals square root of x looks like very quickly. Yep. Half of a parabola on the side. 0, 0, 1, 1, 4, 2, 9, 3, way down here. The parabola's, oops, I didn't want to do that in red. I need to do that in purple. All right, and the graph's going to go like this. Oops, trying to hit those. All right, so somewhere down here, this is going to hit this line up here. That's a bad graph of a parabola. I mean, y equals square root of x. All right, should have looked, as you know, something like that. All right, I was just trying to make it hit my red line up there. All right, everybody got it? You see your bounded region in here? It's enclosed by all these curves. Okay, let's get our points of intersection. The first we have is the green and the purple. The green and the purple. The green is x equals 0. The purple is y equals the square root of x. Well, that's going to be an easy substitution because you just put a 0 in for x. So you now have y equals 0. So this is point 0, 0. The green is the line x equals 0. The purple is y equals the square root of x. So I just did a substitution in for x. So therefore y equals 0. Does everybody see that substitution? Okay, so my next one is the green and the red. The red is y equals 5. The green is x equal to 0. Well, that one's going to be kind of hard to miss, isn't it? 0, 5 is this point right here. Okay? The next one, which went off my page here, is the intersection of the red, which is y equals 5, and the purple, which is y equals the square root of x. All right, what's my substitution here? How are you going to solve this? You are so right. 5 equals, we're just substituting into here, square root of x. All right, that's a radical equation. How do you solve it? Square both sides. So if you square both sides, x is going to be equal to 25. No wonder I went off the page. So x is 25 when y is 5. So way down there somewhere is the point 25, 5. Okay? How are we doing, everybody? Good? All right, you feel more confident in working these problems? All right, and I'll take your questions on that tomorrow. All right, any questions about regions bounded by curves? You carefully make the sketch, shade the bounded region, and many times if you'll use different color pencils, it's easier to see the enclosed area.
Is this section 3.1?
This is called a supplement to your textbook, and it's not in your textbook, but this is a topic that the math department knows you need to know for your calculus course. So if you look at your schedule, it'll call it regions bounded by curves. Okay? That is the last topic that is on your test 1. Excuse me? WebAssign does not have any regions bounded by curves on it, I don't think. Partly because the textbook publishers provided for the provided the funding for putting the questions in WebAssign, and they had to be textbook questions, so we don't have these in WebAssign. Okay? All right. So tomorrow I am going to start out answering your questions, but let me just make sure that we're good with Chapter 2.2 up. And in fact, I think what I'll do is just run to the chapter review. I'm not quite done yet. Got a few minutes. Let's just talk through the, well, where is it? Chapter test to be a good place. Well, we'll go to chapter review. I'm on page 287. I'm on page 287. Or 286. 286 and 287. Just going to kind of go through these things and talk to you about it and remind you of some of the things we did in Chapter 2. One of the biggies in Chapter 2, of course, was your library of functions, your lines, which also were your constant lines. The identity function, I didn't make such a big deal about it. They call it an identity function, but it's still just a graph of a line with slope 0, slope 1 and y-intercept 1. But then we had our square function, which is the graph of your parabola, your cube function, your square root function, your cube root that you guys called an S, that I'll always do that from now on, and your reciprocal function. These were those key functions you learned to graph, and your absolute value function. We did not do, and you're not responsible for, the greatest integer function. Okay, the terms we talked about was a function. Remember, for each value at x, there is one choice for y. You had your functional notation. Y is a function of x. Very biggie. Difference quotient. Are you expecting that on your test? Absolutely. Are you expecting it on your final exam? Yes, ma'am. Very important. Domains, those are associated with which values? X's or Y's? X's. When did you use a vertical line test? Determine if the picture of a function was picture of a graph was a function. Okay, even and odd we did not do. That's not a requirement of the course. How do you tell? Do you have a question?
I just had that on WebAssign.
WebAssign had even and odd questions.
I did some questions with those, so, but I got them right.
They ask you if it was even or odd. Okay, I need to look at those because those are not a requirement. I'll go back and look at those. All right, increasing functions. How do you tell when a function increases? Yep, has positive slopes. The y values increase. Decreasing is going down. What does a constant function look like? Horizontal. Good. How do you find a local? Local means in a little neighborhood. Remember your relatives, local. Maximum, lowest point, and value of the function is just the y value. Ooh, average rate of change. It's your change in y over your change in x. It's your slope. And be sure that if you have words, put words with it like change in distance over change in time so you can interpret your average rate of change. Okay, linear functions were a piece of cake for you guys, best I remember. Is that the end of chapter 2? I guess that's all it did. Alrighty, and then you went, started chapter 3 with your quadratic function. All right, so next time I'll take your specific questions. Have a great rest of the day.